kids, another content video where I'm going to start off doing some practice for our upcoming quiz on definition of derivative. And then I'm going to introduce another topic of reading graphs, how derivatives and their graphs relate to what we're doing. So first, I want to make sure that you can understand these directions and everything that is being asked of you. So here's vocabulary and notation that you are responsible for. So I have to set up a difference quotient. There's going to be at least a rubric point for that. Understanding to come up with g prime of x, that answer, there's got to be at least a rubric point for that. So when I am asked to use a difference quotient to find the slope generator, because there are lots of difference quotients, but I have to use the one that gets me the slope generator. That is limit work, and it's the h approaches 0 one. So in for x, I have to put x plus h minus the function g all over h. Now I have to do some fraction work, right? First thing I notice is I've got fractions within fractions. Ew. So I'm going to turn that division by h into multiplication by the reciprocal. Now I'm going to do elementary school fraction work. I'm going to get a common denominator. So imagine that, right, this denominator is 5 and this denominator is 4. What's the common denominator? 5 times 4, right? And I have to multiply this fraction by x and this fraction by x plus h. So I end up with x minus x plus h. Distribute that negative. X minus x is 0, and I just have negative h. Oh, snap. Look what happened. Since I canceled that h out of the denominator that is multiplying everything, I can go ahead and re-plug in. Plug in 0 for h, and I get x times x, which is x squared. This is my slope generating function of g. That prime means slope. Slope generating function for any x on the function g. So let's go look at this function. I wouldn't have to give you this graph. I expect that 1 over x, you know what this is, complete with its vertical asymptote. So you know that x cannot equal 0. Now, let's go look at slopes here. Can you see, like at this number, right? When x is equal to 1, the slope of the tangent would be negative. How about at negative 1? The slope of the tangent at x equals negative 1 would also be negative. How about way over here? Wouldn't the slopes be negative but pretty flat? How about over here? Negative and pretty steep. Negative and pretty flat. Negative and, hey, all the slopes are negative. Look at your slope generating function for every x on g. You still can't put in 0. Duh, I don't have a graph at 0. And then notice what happens when you put any other x in here. X gets squared, so your denominator is always positive and your numerator is already negative. So this rule, this slope generating rule, says all slopes are negative. So my algebra said the same thing as my graph. OMG. So here's the rubric point I would get for the appropriate difference quotient. I would get 1 to 2 points in here for work, right? And this took a bit of work with the fraction stuff. And then 1 point for giving the slope generating function, because that's what it asked for. Then I was asked to actually find the slope of the curve at a point. So let's go look at when x is equal to 1/2. So when x is equal to 1/2 here, there's the tangent line. What is that slope? Well, g prime at 1/2 is -1 over 1/2 squared, which is -1 over 1/4, which is -4. I expected a negative number, and sure, I could buy that slope there is the magnitude is 4, right? And negative because it's a decreasing linear function. Now, if these directions had just asked for the slope of the curve at x equals 1/2 only, let's suppose I had not been asked for the slope generator function. It just said use a difference quotient to find g prime of 1/2. You might have decided, you know what? Instead of using the x plus h formula, I'm going to use the difference quotient that says the limit as x approaches the x coordinate of the point of tangency. And then the denominator is x minus the x coordinate of the point of tangency. And you just have to put the function first and the y coordinate of the point of tangency here, right? I plugged in 1/2, not to the slope generating function. I plugged 1/2 into the original function. 1 divided by 1/2 is 2. This is the y coordinate of the point of tangency, and this is the x coordinate of the point of tangency. Now this math is actually there's a little bit of hairiness in this graph. I'm sorry, in this algebra. So once again, I have to get a common denominator up here. So what do I have? I have 1 minus 2x all over x, right? My common denominator is going to be x. And then that's going to be divided by x minus 1/2. So again, I'm going to multiply by 1 over x minus 1/2. So you're going to have to recognize that you can factor a -2 out of this numerator. And then I get x minus 1/2. The reason I knew that had to be is because I have to be able to cancel that, right? And I have now the limit as x approaches 1/2. And I'm going to have -2 over x. And the x I'm putting in is 1/2. And -2 divided by 1/2 is -2 times 2, which is -4. And I get the same thing, right? So remember this formula, the x approaches a formula, is only for if you need slope at a point. And in this one, my algebra ended up being just kind of, I think, almost as hairy as the algebra here. So, but that's not always the case. But in the way this original problem was phrased, I had to find the slope generator. They asked me for g prime of x. I had to use the x plus h one. All right, so that's a little bit of practice with that. Now we're going to talk about the relationship between graphs and derivatives. So I kind of sort of started that talk here. Oh, I have a little note. Remember that by difference quotients, we mean for you to use the formal definition. And you can use either form depending upon how the question is phrased. So anyway, I did a little foreshadowing when I was drawing tangent lines on this graph of 1 over x. So looking at derivative behavior. So a warm-up that we will do in class, in our live class, I will ask you to find the derivative of x squared minus 6 using the formal definition. And then I ask you to plug in 3. And we found that, and we will find in our live session, that the derivative, the slope of the tangent on the function f at the x point of 3 is 6. We also found the derivative rule was the slope on f at any x is 2 times the x coordinate. So I want to actually explore the derivative rule. So look at me making a table like I used to do in pre-algebra, right? Here's x coordinates of the point of tangency. And here is the slope of the tangent at those points, all on the parabola x squared minus 6, right? There's x squared minus 6. When x is equal to 3, the slope of that tangent is 6. That's this row here. When the x coordinate of the point of tangency is 3, the slope of the tangent drawn there is 6. When the x coordinate is 2, the slope is 4. When the x coordinate of the point of tangency is 1, the slope is 2. When the x coordinate is 0, the slope is 0. When x coordinate is -1, the slope is -2. Hey, what does the graph of the derivative look like? I think I recognize that. Boom, 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 boom. Right? I just plotted these points and now I see a pattern as if you're, right? And you shouldn't be surprised. Look at the derivative rule. The derivative rule is a linear function itself with a slope of 2. OMG. Check that out. F prime of x. Now let's read that. It's kind of like, I don't know if you've ever been to the eye doctor, right? And they put that funny thing in front of your face and they make you read stuff on the wall and they change the filters, right? And they're like, can you read it now? Click, click. I want you to click your lens to a derivative lens. This graph is a graph of slopes. Graph of slopes on a parabola. OMG. So what's happening? On the graph of x squared minus 6, x squared minus 6, so it's like this, right? When x is equal to 0, there is a tangent line with a slope of 0. Anytime x is positive, the slopes on this graph up here right? Does that make sense? Look at these. Slope positive, slope positive, slope positive, slope positive. And a matter of fact, the slopes are positive and getting larger. How about when your x coordinate of your point of tangency is negative? Over here, tangent line negative, tangent line negative, tangent line negative, but getting more and more negative. What? What is going on? When are the slopes positive, negative, and 0 on x squared minus 6? All I need is the derivative rule, and I can answer that. When are the slopes positive? When 2x is positive. When are the slopes negative? When the derivative rule is negative. When are the slopes 0? When the derivative rule is equal to 0. And you know what? I know when a linear function is 0. Solve it for 0. And then I can figure out when the derivative is negative and positive as well. I don't need you, chart. Thank you very much. When x is negative, the slopes are negative. And get used to this language. You might want to write it in your notes. You don't have to write it like this to me. You can write negative slopes, but you need to be able to read this notation. Slopes are negative. When x is 0, the slope is 0. When x is positive, the slopes are positive. How do I know that? Because I freaking know what the graph of 2x looks like. That's why. I took Algebra 1 and I paid attention. There are some values, some slope values. There is the pattern of the slope generating function. Here is the graph of x squared minus 6. At the corresponding points, look what's going on. When x is 0 on the parabola, the tangent line there, the slope is 0. So when x is 0, the slope is 0. When x was 1, when x is 1, the slope was 2. So when x equals 1, I plotted a slope value of 2. When x was 3, when x was 2, is that 2? 1? Yeah, 2. On the parabola, when x is 2, the y value on the parabola was negative 2. But when x is 2, the slope of this tangent line was 4. So on the derivative graph, when x is 2, I plot the point 4. 2 comma 4. This 4 is a slope value on x squared minus 6. 4. When x was negative 1, the slope is negative 2. When x is negative 1, the slope of the tangent line is negative 2. Crazy. So look at that. Look at what I'm drawing there. Everywhere 2x is positive, there are positive slopes. Everywhere the derivative graph is negative, there are negative slopes. Function decreasing, negative slopes. Graph of derivative, negative. Derivative positive, slopes positive, original graph going up. The original function, when I have a negative slope, the original function is decreasing. When I had a positive slope, the original function was increasing. How do you change from increasing to decreasing? Change from increasing to decreasing means you had a turning point. On the original, what does your derivative graph, though? When your derivative is negative, the parabola was going down. When your derivative was positive, the parabola was going up. What happened when your derivative was 0 and you had a slope of 0? Turning point, not on the derivative, but on the original. Oh my gosh. Reading the graph of a derivative can talk to me about the behavior on the graph it came from. What? Negative slope. Positive slopes. Sorry. Changing from positive to negative passes through 0. corresponded to changing from decreasing to increasing and having a turning point. Wow. We will have much, much more to say about that as we go forward in this unit. And in our live session, we will do a couple more. We'll do a warm-up and some examples of examining derivative behavior, like I did with this parabola and its derivative rule 2x. See you then.